Hello again, everybody. It's time to continue chapter 10. So last time we stopped in the middle of chapter 10 and kind of ended with a discussion of how light is absorbed and transferred and reflected. Now let's jump into what's happening to that light after it gets reflected and absorbed. So the next step in this process is of understanding what's happening on the sort of mechanical sensor side. So if you see at the top of the screen, I have some pictures of satellite sensors. When I'm learning about something new, I really like to actually try and see the physical interface, because for me it helps to kind of understand how everything works. So these are the best images I could find of satellite sensors. So this is an example of a couple of them. I don't have anything up there for scale, but I think they're not very big. We're talking like this, I'm assuming. So those sensors absorb the light that gets reflected off whatever surface is being examined on the Earth. And that takes light in through these various bands over here. Usually we're dealing with 8 bands. In this example, we see 7. And sensors are designed to read one or many bands of the spectrum. That's either panchromatic or multispectral imagery, which we'll get into a little bit later. If we were to look at these with the naked eye, they would look grayscale, as they do here. And if you notice, within each of these images, there's kind of varying brightness in the different parts of it. So we've got like dark gray, we've got kind of bright, almost white, down to black. These are called brightness values, and we'll see what those mean in the next slide. But each brightness value has a corresponding numeric value. So in the next stage, of course, you take these images, these kind of black and white looking images, and you push them through these different colors, and you combine these different colored layers to create composite color images, which you see here. So this is simplified, but let's continue on and get a little bit more into what this all means. So let's talk again about what's happening with that sensor when it's taking in information. It's not only taking in light waves that have been reflected and are being absorbed, it's also taking in spatial information. So this is a word that will come up in the chapter and later on. It has a spatial resolution, which means that each square that you see here, each pixel or raster is a word that keyword that we'll be using later on, actually represents a physical location on Earth. And when you look at these images, each square has its own brightness value. So what has happened is the sensor has taken in the light and it's generalized the value of that brightness for that particular square or spatial resolution. In this image here, we're seeing squares that represent 250 kilometers, 100 kilometers in width, and 28 kilometers in width. Let's talk a little bit more about these brightness values. So typically the sensors we're working with are have 8-bit imagery, and that is going to give us brightness values on a scale of 0 to 255. So if we take this little table here, this little mosaic, it looks like we have different shades of black, gray, and white. Those are assigned those numbers I was talking about. So 0 over here would correspond with that, which means it's black, whereas the one above it is almost all white. It looks like we have a 255 here, which is at the other end of the spectrum scale, which means it's completely white. So these are important because this is going to feed into how the numbers are then correspondingly read through the color gun, which we will discuss here in just the next slide. So how do we get from that sort of seemingly grayscale to these color bands? Well, remember that these color bands are actually reading specific wavelengths. So even though they look grayscale on that one side, they're actually targeted to read just a certain wavelength. So how we actually get that to look something that's familiar to our eye is we transfer it through what's called a color gun. Now, color gun isn't actually a really kind of archaic term for what they used to do with old television sets with their tubes, with the television tubes. They would put colors on it and they would transfer the radio. I don't really know actually how it happens, but that's where they get the term from. So what's actually happening is a lot more complex than that, but it's the same kind of concept where you're transferring an image through a color to project it in that color. So instead of seeing black to white in grayscale, we're seeing white to the darkest red with all different shades of brightness or pale reds in the middle, or blues or greens. Now, if you guys have ever worked with say you've gone into Word or PowerPoint and you've tried to play around with the color of something, you might have gotten into a screen that looks like this. This is using basically the same concepts. You're mixing red, green, and blue, otherwise known as shorthand as RGB values, and you're getting these various shades, different kinds of brightnesses along this whole spectrum. And when you put these together, it creates what's called a composite color. So as I mentioned before, this is called multispectral imagery, so we're seeing different kinds of aspects of the spectrum. And they can actually just do one color. I say here that I talk about the panchromatic image, which would actually just be grayscale. But you can actually have anywhere from 7, 10, up to 36 bands. That's when your imagery starts to get much more complex. You can do some fun analysis with it. Again, these color bands are added together to create a composite image, and you can see here a good example of how these are transferred via their color guns. So the interesting thing that's happening here is not only are the sensors reading things at a certain frequency or a certain reading a certain wavelength. When you get further into imagery analysis, you can actually transfer those wavelengths through a different color gun and get different kinds of imagery, and that's where we start later on learning about infrared imagery and reading that in different ways. Okay, so that was chapter 10. Now let's move on to chapter 11. Let's talk about those satellites. So we went from our GPS satellites and learning where we were and those signals and how that all worked to understanding actually how we see things, how those satellites with their sensors actually see the reflected light off the Earth and how that becomes imagery. Now let's learn a little bit more about how those satellites work, because it's, as all things are, a little more complicated than one might reasonably expect. So let's look at it from the macro perspective. Let's look at satellite orbits to begin with. Satellites don't just go in one direction around the Earth, they actually go in multiple directions and for multiple reasons. Our three main kinds of orbits are sun-synchronous, geostationary, and polar orbit. So let's go into what those mean here. Near polar orbit, I will get out my handy dandy globe here. That means it's off. The satellite is circulating around the globe, almost around the poles, but not quite. It's off by just a tiny bit. So it moves in the same pattern like this around the Earth, but what's happening, of course, is the Earth is turning. So as it's going around, it's capturing a different image of the Earth, and then eventually it will come back to the same spot. So that's a near polar orbit. It takes approximately 90 minutes for it to complete one orbit. Now let's talk about geosynchronous orbit. What's happening there is a satellite is shot out a mere 22,238 miles away, and it goes into orbit and it stays to the observer in the same spot. So what it's doing is it's staying in the same spot relative to a place on Earth. So if the satellite's here over North America, as the Earth turns, the satellite is going to stay over North America. So it'll always be in the same spot. This is good for communication satellites or places where you need a constant, reliable satellite feed. And last, we have sun-synchronous. This is really good for the imagery. So near polar is great for taking environmental readings. Geosynchronous or geostationary is good for communication, and sun-synchronous is good for taking bright daylight imagery, because what happens is the camera is actually, the satellite rather, is following the sun as it orbits the Earth, or as the Earth orbits it. It's sort of imitating a stationary sun, so that basically it's staying in light all the time as it goes around, as the Earth passes underneath it. So when the satellites are gathering data, in general, how it works is as the satellite orbits, the camera is facing down onto the Earth, onto a certain little area, and it creates what's called an observing strip, or swath width. And this is a set distance that is used to calculate the size and the spatial resolution of the image that's produced. In this case, we generally have an observation swath width. That's kind of a tongue twister, of 185 kilometers, and that's divided into 30 meter by 30 meter squares, which is the spatial resolution that we're talking about. And it's important to note that there are two kinds of sweeps they can do. Satellites can scan back and forth like this, so sort of on the short end, or they can just scan front and back this direction. So let's talk about resolution. Resolution is important to remember. It's going to come up in your homework for the chapter. Radiometric resolution is the amount of bands and data that it's taking in. So I talked about 8-bit resolution producing 0 to 255 brightness values. That's the radiometric resolution. It can be very coarse, like down here, or it can be very fine up here. But this is going to give you, however, what the radiometric resolution is going to determine the fineness or the granularity of your data. There's also spectral resolution. So as I mentioned before, those bands are designed to take in certain wavelengths, and that's the resolution of the camera or of the sensor, the spectral resolution rather. Temporal resolution just has to do with how many times a sensor or a satellite will pass over a given point. Some sensors pass over the same point every 24 hours. Some sensors will pass over the same point every 11 days or 3 days or not. That's the temporal resolution. And finally, the spatial resolution is what part of the physical part of the Earth is the sensor actually taking a picture of. And to make it more complicated, spatial resolution can actually change depending on the spectral resolution that the actual lens the sensor is taking in, and that can vary depending on the kind of image that it's capturing. So you can see here, this shows just how the different sensors have different resolutions and how that applies. So we have our temporal resolution here. This one comes around to the same spot every 12 hours. This one every 16 days. This one every 22 days. So there's a lot of variation. And so what happens to all this data? Well, once it gets captured by the sensor, it gets then relayed down to the downlink sites that are all over the world. We have one in the United States. There's obviously another one up in Canada here, but this one is actually in Sioux Falls, South Dakota. So it's actually not too far from Wyoming. Just a few facts about Landsat 7 and 8. They both maintain a near-polar sun-synchronous orbit, and they follow the World Reference System. They each make an orbit in about 99 minutes and complete over 14 orbits per day and provide complete coverage of the Earth every 16 days. And there's an 8-day offset between the two satellites. The descending daytime node from north to south crosses the equator between 10 a.m. and 10:15 a.m. on each path to provide maximum illumination with water vapor, haze, and cloud buildup. So as you get further into your GIS career and we start looking at more satellite imagery, you'll notice that there's going to be a lot of imagery that actually isn't really usable, and that's because of the weather and because of clouds. And that's why it's so necessary to actually do so many sweeps and analyze your imagery closely. So how do we read the data? Again, let's look back at this swath width here, which is not to scale, I might add. You can see how it's imitating, though, how it's showing you how each sweep kind of is covering North America. Day 1, day 2, day 3, day 4, day 5. So it gives you some idea of it's just literally scanning the Earth, one section at a time. What's important to know about this is what this is called. This is called path and row, and this is a reference system that is often used with Landsat in order to identify what image you're actually looking for. So if we look at this illustration here of Ohio, you can see that Ohio is covered by paths 18 through 20 and rows 31 through 33. And that is actually the size of the images that are taken as it's going over. And from all of this wonderful satellite imagery, we get not only normal pictures of the Earth, sort of the color that we would expect to see, but we get all of this scientific infrared data that provides just loads of valuable information about air quality, about CO2, about weather patterns, about temperature. Um, there's so much that can be done with it, and we will explore that a little bit more later in the semester. So that is it for now. Enjoy the assignment for the week, and I'll talk to you guys later.